Gotta get through this lecture, and I'm trying to make it so we make it work. Let's put numbers to all this to make this happen. Let's imagine we were trying to predict a person's GPA by the attitudes they may have towards education and the education of one of their parents themselves, educational level. Right? So perhaps we run analysis right here, and we see that we get an intercept of 30, a main effect for education or attitude of 1, a main effect of education of 2, and a two-way interaction of 0.5. So, given any values of the predictor variables, this model equation provides predictions for the value of the outcome itself. Right? So we always talk about what a person's value of their GPA, predicted GPA, would be. And actually, in this case, I think GPA would be on like a 100-point scale. We could also get from that any conditional main effects of the main effect of the model itself for each of the variables we put in. Right? So what a conditional or simple main effect happens to be is the value of the main effect plus whatever is going to modify it. I'm going to show you this in just a second here. So, for instance, if we wanted the main effect of attitudes, where does attitude show up in our analysis? It shows up here as a main effect, and it shows up here as an interaction. So the first step in figuring out how to come up with a conditional main effect is to go and pull out all the terms of the model that involve attitude itself. Right, so we've got beta 1 times attitude plus beta 3 times attitude times education. The next step, if we look at that, we can factor out the common predictor variable itself. Right here, in this, attitude is the common predictor variable. So we could just factor that out, have it multiply beta 1 plus beta 3 times education, and then for any level of education, what's in the parentheses represents the value of its main effect conditional on education itself. Right? So if education itself was not centered, if education was just left to be whatever, then beta 1, or 1, represents the increase in GPA for every 1 unit of attitude when education is equal to 0. But what if we wanted to talk about someone with an education of 3 years of school or something like that? Right? Then the main effect for attitude would no longer be 1. Right? By this formula, the main effect for attitude would be 1 plus 0.5 times 3, right? Or 2.5. Right? So for somebody whose education is a value, someone who has 3 years of school, their GPA goes up by 2.5 points for every 1 unit of attitude. Right? So what we see there is a brand new effect itself. And one way we can do this is trying in values. We can plug in values for education and get a new main effect of attitude, or vice versa. We could go to attitude. We could look at education as a function of attitude itself. We could plug in different values of attitude itself. But we're going to use the software to be able to do this for us in what we do. But for us, let's try this with a new reference point. Let's assume that we want to go and essentially center our model for attitude equals 3 and education equals 12. Let's see how that happens. So, this is why 0 matters. If we look at this here, Y is our student achievement, so GPA out of percentage as a percentage out of 100. X represents a parent's attitude about education measured on a 1 through 5 scale. Z represents father's education level. This is a terrible example of father. Who cares about the father? But let's just call that education of the parents, whomever. And then we have all of our regression lines here and all the numbers that we saw before. Interpret these. We could interpret the intercept that represents, in the slide that we saw before, 30 represents the predicted value of GPA for someone with no attitude, or it's measured on 1 to 5. So attitude of 0, which is below the floor of the scale. and for education of 0 years. It's also kind of hard to find for most of the data we collect around here. So that 30 is a really odd number. It doesn't have much meaning. Beta 1 represents the increase in GPA per unit of attitude for someone who has 0 education. Also an odd number, right? Beta 2 represents the increase in GPA per year of education for someone with an attitude of 0. And the interaction either increases the effective education by 0.5 for every additional unit of attitude, or when education is the moderator, increases the effective attitude by 0.5 for every additional year of education. All right, so that's where that interaction can go in either direction. So what would happen? What would be the predicted GPA for an attitude of 3 and education of 12? It'd be 66. Right. 66 out of 100. I don't know. Is that good? I guess. But what if we went and changed our model so that we centered education at 12? Right? Well, the prediction has to be the same. What has to change to give this? Let's take a look. Right. So here, these are the new coefficients that would be. And what happens is we know that we've taken 12 away from education in each of these spots. Right? So here in education, the slope for education doesn't look like it changes much. Why does the slope for education not change much? That's a little weird. That's because the scale of the predictor attitude, the thing that it modifies it, and the interaction didn't change. What changed was education, right? So that prediction is the same, but over here, our slope for attitude now changed. The slope for attitude changed because where 0 is on education shifted, right? 0 for education is now at 12. So that's 12 units away, but the effective education is only 1/2. So 1/2 of 12 is 6, and that's where the difference from 2 to 8 happens to be. And to make up all of the numbers, we have to kind of modify the intercept to be 42 to shift the whole thing up 12 overall. So so basically what we're saying is to change all this, we plugged in 12 and we did the same thing we did before. If we were trying to predict somebody with an education of 12 and an attitude of 3, we'd still make a 66, right? This would be 0 now. This would be 0. And we would get 42 plus 3 times 8, which would make 66 altogether. Right? So we still get the same predicted value, but certain things change when we modify which predictor the 0 point happens to be. Similarly, for what would have happened if we would have switched attitude? Right? If we centered attitudes at 3, can you predict what would happen to this line? So let's start. Would the intercept have changed? Actually, let's start with that last. Would the interaction effect itself have changed? How many say yes? How many say no? How many abstain? The voter turnout is very low in this place. It's just like my beliefs about politicians, right? I don't like any of the statistics. I get it. It's okay. Maybe that's not it. Would the effect of education change? Yes, because what's interacting with it just changed at 0 point, right? Would the main effective attitude change from 8? No, because what modified it, education, hasn't changed. And would the intercept change? Yes, it would have. So here's what we end up getting. So, I just had this slide. Why is that back there? There we go. Old equation for uncentered predictors, now the new equation with the centered predictors you see right here. 66 is the value of the intercept. That's the value when everything's equal to 0. This attitude minus 3 is equal to 0 when attitude equals 3. Education minus 12 is equal to 0 and education is 12. All right, so that's where we get all of our numbers. If we talk about the effective attitudes, we see that the effective attitudes when education is 12, so that's a person who has 12 years of education, maybe like a high school degree, right? So their attitude, for every one more unit of attitude that goes up positive about education, a person's GPA would go up 8 points, right? So if you got someone who dropped out in 10th grade, that effect would be smaller, right? In fact, what this is saying is the effect of attitude increases with education, right? So for every one additional year of education, the effective attitude goes up a half point. So if you took someone who took 4 years of college, that now is 16, the effective attitude will be 4 times 0.5 plus 8, or 10. Right? So it's an even stronger increase as it goes along. Devane, you have a question?
This may be me reading way too much into the model, but I'm feeling like this gets biased the moment you have someone say they got a high school degree, but they were held back a year, so now their education is 13 instead of 12.
Well, I mean, it depends on how many. Yeah, I don't know. I mean, that gets a little more in the nuance of it. I think this is assuming that never happened, right? Let's just go with that. If you have data like that, if you've got, maybe you put in high school degree as a covariate as well, right? So now somebody who will have 12 years of high school would also be modified, or it might interact with whether or not you have a degree at the end of 12 years, or if it took you 13 or 14 years, or longer for that matter. But yes, I mean, ultimately, the data that go into it have to be accurate to describe it, and if there's other variables, that's kind of an omitted variable problem that you bring up there, at least the way I look at that. So that was the effective attitudes. We saw that. The effective education is similar. When attitude was centered at 3, the effective education is 2.5. Right? That's what we see right here. Right. So the effective education increases with attitude as well. Right. So it's another positive relationship. That's what that interaction is doing for us. Now you'll note the thing that's unconditional here is the highest level of the effect. That's the interaction. The interaction is true for everybody's value of education and for everybody's value of attitude itself. Fun times, huh? All right. So we can test for this. In fact, what we might want to do, if we look at our p-values, right, each of our software packages gives us a p-value for the effect itself, right? So if we ran an analysis where we estimated things without centering, and we compare that with an analysis where we estimated things with centering, we may see, in fact we will see, different p-values for the intercept and for each of the main effects, because they're different places now, right? So ultimately, every time we want to talk about the level of an effect, whether it's conditional on 0 or whether it's at some specific level, for instance, if we want to talk about the effective attitude when education was 12 or 16 or some other critical point, we could go and figure out what the effect happened to be, but from it we'd also be able to get the standard error of the estimate and do a t-test or a Wald test on it, right? We could go and figure out whether or not that effect was significantly different from 0. And it's going to be the case, because of the way the analysis works out, particularly in a place with quantitative predictors, that there will be what we call regions of significance for the main effects themselves, right? So for instance, it may be the case that this 2, that if we looked at this analysis to begin with, maybe that's not significant. Maybe the p-value is 0.25. But we may see that 8 is significantly different from 0. Right? So what we'll see is for all the levels of education, there'll be some levels where the main effect of attitude is significantly different from 0, and some levels where it won't matter at all. Right? And that is essentially an additional descriptive of how you understand the interaction effect itself. What is the interaction doing to the main effects? By the way, I opened this window. Are you guys okay for heat and temperature? Okay, just making sure you're taking one for the team, because everybody else is very hot. So if you're cold over here, okay, please change seats. Or we can try to find another way to cool the room a little bit. Any questions on this? This is complicated material. Okay, so how do we go and do that, though? So any of us can go and add these numbers together and calculate the new effect, right? For any level of attitude, we can calculate the new effect. The harder part is figuring out what the standard error of the effect is, because that's what gives us the t-test itself. So how do we figure out the standard error of the effect? This is where most of the time we just want the software to give it to us. All right? We can do this with this ugly looking function GLHT. Glut. Glut. Would you pronounce that differently? I don't know. General Linear Hypothesis Test. I think that's what it stands for. GLHT and R. If you're in SAS or SPSS or M+, even there'll be different versions of this. But the standard error itself can become, you could do it in the software, which I prefer. I like this option the best because the original model, I like one model to contain all the information. I don't like to have to recenter things or do other things to it. So if I can keep one model, I'm happy. The other thing is to recenter and rerun the analysis. So if we centered attitudes by 3 or so forth, we would be able to re-estimate things. That's fine too. The third one, and I really don't like this one enough because we could do it by hand, but to do it by hand, the new standard error comes from like the square. If you take the standard error and square it, it becomes like a variance. And the way we get the squared standard error is to take the value of the first variable standard error, the value of the second times the predicting variable, and 2 times the covariance between the 2 times the predicting variable. That's a mess, right? First of all, I can see where we can get these. These are standard errors squared. Have you ever had the software give you a covariance between parameters before? Not going to happen very much, right? You can go and figure out an option in each of those packages, and it'll give you not only the standard error for each variable, it'll give you the covariance between parameters, which is a little weird to think about what that means. But to figure out what the standard error happens to be and to do it properly, we'll need this weird combination where we have the covariance involved with it as well, and that's why doing this by hand is a terrible idea. Apart from just me being lazy. I don't like doing anything by hand anymore. No, just kidding. I was going to think brushing my teeth, but I've got to, like, the remote operating. I use a razor. Oh, that's it. The shave. But would that be called shave by hand instead of like an electric razor? No, I don't know. Anyway, point being, that's what we're basically doing. We're trying to automate this a little bit more. So here's our first example. Let's imagine we take that original data from before. Actually, let me back up. Any questions before we go on? Why this happens, we will discuss in a few weeks when we get to random variables itself. It involves linear combinations of variables, and so when things get correlated with each other, we have to keep track of that when we go and make combinations of the terms. But for right now, just know it's a mess. Okay, so let's imagine we want to go and do our example model, model 1 in this case, where we have our data of the proportion, right, or test scores for seniors and freshmen and new ways of teaching and old ways of teaching. So I can run this analysis. If I go to my R syntax and I run all of the lines up to, I think, line 54. Oops, went too far. Up to line. I'm going to stop right up here. This basically does all the stuff that we saw in the slides before and gives us standard errors. This first line of syntax, can you all see the syntax well enough, or do you need it bigger? I don't have many parts of me that work well, but the eyes do, so I take that for granted. Is this better to read? Okay. The eyes haven't failed me yet, but that's probably coming. So what we do is we run this line of syntax, and if it runs, you'll see model 1 show up down here in blue, and there won't be any errors. In fact, let me zoom in again down to the bottom. Model 1 will be at the bottom. So it's like, dude, where's my statistics, right? Where'd they go? Did it run? Did it work? And in R, they like to sort of make you work a little harder than that. You have to ask for summaries of the statistic itself. And so you see the word summary in Model 1. So all the information about this analysis shows up in Model 1 now. Right? That contains everything. So now you have to ask R politely. Summary is a way of doing it. When you click on summary, what you should see in the box below is a bunch of information. Something about residuals. We're not going to worry about that yet. But here are the coefficients. These are the regression slopes. All right, so here is our intercept, that is the mean of the reference group. Our conditional main effect of senior, our conditional main effect of new, and our two-way interaction between the two. And just like you'd see in a regular regression table, you'll see a standard error. The parameter estimate divided by the standard error is the t statistic. And then this thing compared to a t distribution with a certain number of degrees of freedom gives us the p-value. Right? So it also gives you some other terms. Down here, your r squared, for instance, that's a nice one. Residual standard error, that's the square root of the variance of error, of the residuals. That's nice. So that's one way that you can see things in R. Another thing you can do if you really wanted to get fancy, if you type plot and put model 01 to it, and hit enter. Uh-oh, what did I do?
Model 1 without the 0.
Oh, thank you, Devane. Yeah, man. Come on, Templin. Okay. Over on the bottom right section of RStudio, this is one of the nice things about RStudio, is under the plots tab, we'll now start to see plots show up. Like here is residual versus fitted values. You might see a QQ plot. What? These plots are nice, but they take a little description. Basically, each of the things that R builds in Model 01 has a bunch of hidden stuff to it that you can sort of use R to bring about. For our purposes, though, the summary statement works pretty well. And the other term that works pretty well is the Anova statement. The Anova statement takes that summary that looked like a regression table, or looked like a regression coefficients, and puts it into an Anova table, something that we have seen in many of our stat classes before. You've got a line for each of the effects, the degrees of freedom of each of the effects, sums of squares, mean square, f-tests, and so forth. This is, by the way, something that's going to be going away from us. Our models won't have these anymore. What we do. Questions? Okay, let's go back to the slides. So there is our model. This is kind of what I'm trying to do in the slides to bring about the key sections of syntax to look at. To run this analysis, we needed to say LM. We put our dependent variable first. We put a tilde. And then we put each of our predictor variables. And we had senior times new listed afterwards. And finally, we'll note that data, this tells us the data set, data 01. So if we were to open up that data set, data 01, we should see each of those variables in it. So if we went back to RStudio, went over to the right-hand side, just double-clicked on the data, we should see each of the variables we saw. Test, new, group, and senior are all showing up together. Okay. So the next thing we can do from R is get each of the means themselves. Now, we could have gotten the means in other ways. We could just ask for the mean of each of the data. In fact, up in the top of my syntax, I got the mean differently. But here in R, I create these 4 variables in R called means. And they're not really they're sort of weird. Remember, R is this object-oriented language, which means every time I type a line of syntax, like mean 1 equals, and I put this set of code to it, it creates an object named mean1. And for us,